Hi, good morning, everyone. Today, I will introduce our research on undetectable data reconstruction attack on vertical federated learning. I'm Duan Yao, and this is joint work with Song Zeli, Xuelan Gong, Si Zaihou, and Gao Ningpan. And let me first briefly introduce what is vertical federated learning. So basically, vertical federated learning is a collaborative learning paradigm where data are distributed across multiple clients. And here is only one active client who holds labels and partial data features. And there are also multiple passive clients who holds other data features. And during training, each client will hold a bottom model for computing the local data features to compute embedding. And also the active client also hold a top model for final prediction computation. And VFL protect privacy by just sharing embedding rather than raw data. However, VFL is not as secure as it appears, because if the active client is a malicious adversary, he can infer or try to reconstruct the original data features from the received embeddings. This is what we call data reconstruction attack. And data reconstruction attacks usually fall into two categories. The first is honest but curious adversaries. These kind of adversaries can extract private data features but still follow the training protocols. The second one is malicious adversaries. This adversaries is more strong. He can manipulate or violate the training protocols to steal the private data features. And our work will focus on this kind of malicious adversaries, since it will pose greater threat, but less previous work explored on that. And here is our threat model. We consider three capabilities for the adversary. The first is that the adversary is the active client. And also the adversary is malicious adversary, so it can violate the VFL protocol. And the third is that the adversary can access a small set, it's just a small set, an auxiliary data set which share similar distribution with the training data, but distinct from it. However, launching effective data reconstruction attacks will face two main challenges. The first is distributed features and limited model access. It's that the target class model is black box for the adversary. And also, the data feature space is quite heterogeneous and distinct from the ones the adversary holds. So it's really hard to infer, the other space, the data features. And the second challenge is that since malicious data reconstruction will alter the VFL training task, so it will be easier to be detected by just comparing its gradients from those gradients from the honest training. So current detection method like speed guard and gradient screenizer will be effectively identifying this kind of malicious attacks. So for addressing these two main challenges, we propose our method URVFL and URVFL sync. And it basically contains three steps. The first step is pre-training, which includes training an encoder-decoder structure. The second step is malicious gradient generation, which we will introduce our key innovation DAC. And the third one is data reconstruction using our trained decoder. So let's just first step into the pre-training phase. And this phase is used to train an encoder-decoder structure to recover the target data on auxiliary data set. And this step is used to train the encoder to produce similar embeddings with the target models would generate. And also we will train the decoder to learn to recover the data from the received embeddings. So after pre-training, we step into the malicious gradient generation, and this step is used for transferring the embedding distribution from the encoder to the target model. And here we use a really novel structures It's discriminator with auxiliary classifier, or DSA for short. And DSA will help, not only DSA will help differentiate the embeddings from different sources, it also can incorporate labels informations. So it will guide the target models. It will generate malicious gradients to guide the target models to mimic the embedding distribution from the ones in encoders, and also keep the gradients undetectable by the detection methods. And the third step is just data reconstruction. We can use the trained decoder to reconstruct the received embeddings. And because of the embedding distribution is quite similar between the target model and our previous encoder, so the decoder can be really effective to do the reconstruction. And you may wonder why we use DAC. Why not just use a standard discriminator? That is because the standard discriminator just minimizes the JS distance between the embedding distributions, and it will ignore the label informations. And there are two shortcomings. The first one is ignore the label informations. And the second one, the label information may help us to do the embedding transferring. So ignoring label information may degrade the embedding transfer performance. And the second one is that it makes the gradients easier to be detected. So that's the reason why we use DSA. It's because DSA will minimize the joint distribution of embedding and labels, and it will make the gradients less detectable by the current detection methods, and also improve the embedding transfer performance. So here is a visualization of the embedding distribution of standard discriminator and our DSA. So the leftmost figure is the embedding distribution of credit and minutes dataset respectively, and the middle row is the embedding distribution generated from standard discriminator. And the rightmost row is the embedding distribution generated from the DSA. And you can clearly see that if we use the DSA, the embedding distribution will be more similar with the original one. And also the cosine distance, you can see that it will be lower. For example, the cosine distance is 0.02 compared to the 0.04 generated by standard discriminator. So it further confirms that incorporating label information will further improve the embedding transfer performance. And here we measure two aspects of our attack. And to measure embedding transfer quality, we use embedding MSE distance and cosine distance. And to measure the reconstruction, we use MSE across all datasets. But we also use PSNR and SM for image dataset to better evaluate the visual quality. And here is our tabular dataset results. And you can see that our attack can outperform all the other baselines consistently. For example, URVFL can achieve 0.42 reconstruction error compared to the suboptimal one, FSG, which is 0.5. And also, our attack outperform other baselines in image dataset, and you can see that for safer turn dataset, our sync, the URVFL sync is a variance of URVFL, and its reconstruction error is 0.01 compared to the suboptimal one, FSG, 0.03. And also, SM and the PSNR results also show our superiority of our attack. And crucially, it says our attack can keep consistent performance even under the detection like SG and GS. And you can clearly see that for other attack, malicious attack like AJN and FSG, it will drop a lot. It will drop a lot when facing the detection. Like it will drop from 22 PSNR to 10 if facing the SG. And also the detection score. Also, we show the detection results when the results when there is a detection. You can see the orange line is the detection score. If it's above the threshold, it indicates that our attack can successfully embed the detection. So you can see that URVFL consistently above the detection threshold. And other methods like FSG, they fall below the threshold, which means it's easily being detected. And also there is visualization. You can clearly see that URVFL can achieve better reconstruct quality compared to other methods under and without any detection method. And if there is detection, and AGN and FSG will cannot reconstruct any meaningful pixels. And here is the conclusion. Here is the conclusion. It's that we propose URVFL and its novel attack can circumvent all the detection strategies, and we should also pay more attention on the malicious attack because it will pose more privacy leakages. So for future work, we may try to defend this kind of malicious attack. Thanks for your attention. I'm happy to take any questions.
Thank you so much. Questions, please. Yep.
Thank you. And do you have tried beside the image data to? I think because on the vertical setting, I will assume each feature has a totally different distribution. But in this case, you just split your image into different blocks, and in that case, I will assume there are more correlation between each block. So have you guys tried to attack on the vertical setting with using dataset from image, beside images? Yeah.
Thanks for your question. And we just tried the dataset on tabular and image dataset. So maybe in the future, I want to try the text dataset to test its performance on language models, but just tabular dataset. But I think tabular dataset there with less correlation between each block of the data. So maybe, and also our attack can perform very well on that dataset. So maybe it can work in text dataset. I will try. Thank you.
All right, we are almost at the end of the session. Thank you so much. Let's thank the speaker.